So mostly multiple choice and then a little bit of free response questions. There will be some bonus questions on the final exam. The finals were the big chunk of the grade, 200 points. But there'll be some opportunity to earn some bonus there. Which will lessen the impact. I had a question earlier from chapter 16 that I thought I should probably talk about in this class as well. It has to do with the titration problem. Number 102. Normally I try to assign the blue ones because the blue ones have the solutions from above. But this one, I think I signed this one, 102, did I? You guys already do this one? 102. Or did I not assign it?
Oh, you did assign it.
Yeah. The reason I assigned this is because this is in Chem 1A you have to do titration. And this is the titration that you do. You're titrating oxalic acid dititrate. That's the acid. But this acid's a bit different. You know, in your titration, you had an HCl solution. This is a solid dichroic acid. And so this is a stable hydrate. Solid. There's also the anhydrous form of oxalic acid. So I want to talk about this one since the solution's not in the book. But this is number 102. And oxalic acid has some strong intermolecular forces holding it together. You know, for example, HCl at room temperature is a gas, it's hydrogen chloride gas. And then there are some that are liquids, and then there are some that are room temperature solids. This is a room temperature solid, which means the intermolecular forces must be quite strong. And the first thing is, what are the intermolecular forces on oxalic acid? So if we look at the Lewis structure for oxalic acid, it's like this. And so can you list the intermolecular forces holding oxalic acid molecules together? What intermolecular forces do we expect? Well, the bonds are what we call intramolecular forces. Intra is within, so the covalent bonds hold the atoms together. The intermolecular forces hold the molecules together. These molecules are somewhat sticky. So if this is an oxalic acid molecule, then it gets stuck to another oxalic acid molecule here, and then to another one here, and then to another one here. And then we build up, what is this called? We build up the solid this way. And the solid would be called a what?
Crystalline?
Yeah, it's crystalline. And a crystalline solid would consist of a lattice. So this would be a crystalline lattice of oxalic acid molecules. What holds oxalic acid molecules together? There are no bonds that hold it together. There are no covalent bonds or ionic bonds that hold the molecules. These molecules are stuck to one another, and they're sticky to one another because of intermolecular forces of attraction. So what are the intermolecular forces of attraction that hold the oxalic acid molecules together?
It's all three of them, right?
All three of them. Three of them, what are the three?
Hydrogen bonding.
Hydrogen bonding, which is going to have a big dipole here, and
It's like induced dipole.
Induced dipole or instantaneous dipole.
And then just dipole.
And then dipole. We have regular dipoles here. A regular dipole would be this carbon-oxygen. These carbon-oxygen double bonds in organic chemistry are called carbonyl groups. And these alcohol groups are called hydroxyl. And when we have a carbonyl and a hydroxyl, we call it a carboxyl group. It's a carboxylic acid group. But this would be an unusually big dipole. Unusually big dipoles are called hydrogen bonding. And then this is a regular dipole. And then we have instantaneous dipoles. And all three of them hold these together. And so at room temperature, they're so sticky that they're locked in a crystal lattice like this. When we have a crystal lattice like this, there are empty spaces called void spaces between the molecules. And sometimes another molecule can fit inside that void space, and in this case, water. So if there's water in the air, the water can wiggle into the crystal and get stuck. And so here's a water that gets stuck inside the crystal lattice. And for every oxalic acid, we have two waters that get stuck. So for every one of these molecules, two waters get stuck in these void spaces. Sometimes we can fit more waters, sometimes we can fit less waters. But this is the maximum number of waters that fit inside here. And so this is kind of like a sponge, and the sponge has been saturated with water. And so this is a stable hydrate. It's not going to pick up any water molecules, because 2 is the max. And it's not going to lose any water molecules. It won't lose it unless we have dry air. Actually, this will be the crystal here. If the air is not humid out here, it's very dry, then some of these waters might vaporize into the air. The anhydrous form, anhydrous means no water. Anhydrous oxalic acid is not stable in humid air. If I have anhydrous oxalic acid in humid air, it sucks the water out of the air. Things that suck water out of the air are called desiccants. And so anhydrous oxalic acid is totally desiccated. And I have to make sure that the air is totally dry. And so if I have anhydrous and I want to keep it anhydrous, I have to store it in a humidity-free environment. So I have to make sure. Otherwise, if there's any humidity, then the humidity in the air, the water molecules in air will wiggle their way into the crystal void spaces and get stuck like they are here. So when I weigh out first thing is, this is a stable hydrate. This one is not so stable in humid air. So if I try to weigh this stuff, this is no problem to weigh. This is a problem to weigh. So if I were inside lab and I scooped up some oxalic acid anhydrous and put that on the balance, do you know what's going to happen to the weight?
It's going to start increasing.
It's going to increase. It's going to start increasing because it's going to start absorbing water from the air, making it heavier. Because as the water molecules get stuck in there, then we're weighing the whole thing. And so we're going to have 2 molar masses here. We're going to have the molar mass for the hydrate and the molar mass for the anhydrous form, depending on which form we have. In this particular problem, we have the hydrate. Now, oxalic acid dihydrate is a solid diprotic acid that can be used in the laboratory as a primary standard. Have you heard of that word, primary standard? Normally we have standards. And standards are things that with well-known, composition. Those are standards. Did I talk to you about the peanut butter standard at the NIST? I was watching this YouTube video. And, they're interviewing scientists at the NIST. in Washington, D.C., I think. The NIST stands for the National Institute of Standards and Technology. And I had no idea they sell things. Yeah, I didn't know they sold things. I thought they were just interested in keeping standards. Like what is the kilogram, etc. One of the things they sell is peanut butter. And so they showed some jars of peanut butter. These jars of peanut butter turned out to be very old because they had made them a long time ago. But they were also very expensive. I think he said it was like $6,000 for a little jar of peanut butter. And why was it so expensive? Maybe it was 16,000. I can't remember. It was 6,000 or 16,000. Why it was so expensive is because they analyzed every single chemical inside that jar of peanut butter and quantified it. So they knew how much and what was in it. And so what they do is they have this, they call it the standard peanut butter. So you can use that standard peanut butter to analyze your own peanut butter to see, how much of this fat, how much of that fat, how much of the salt, And so they use that standard for analysis. Well, a primary standard is something with a well-known composition. So you can get this in high purity. But one thing we need for primary standards is high purity, so we know what's in it. The other thing is a primary standard has to be in a reliable weighing form. And usually primary standards you have to be able to weigh. We need to weigh them because we can measure weights accurately, and that is masses. But measuring volume is not. And so if we had to measure the volume, like in our HCl solution, we measured it by using the burette to measure how many milliliters. That wouldn't be a primary. That would be more of a secondary standard. And so primary standards are often used. And so what is a primary standard? For example, there are two categories of analytical standards. Primary standards and secondary standards. The primary standard is a reagent that we can use to dispense an accurately known amount of analyte. So high purity potassium dichromate, we can weigh that, we know how much it contains. Versus a secondary standard is hard to measure out. A primary standard is a reference chemical used typically to measure unknown concentrations of another known chemical. It can be used directly when performing titrations or used to calibrate standard solutions. Standard. And so we can buy these at NIST. I'm sure NIST is very expensive. You can buy them at a lot of chemical manufacturers make their own standards, primary standards and secondary standards. All right. And so rather than measuring how many milliliters of HCl solution, we're just going to weigh this. We're going to weigh how many grams of oxalic acid dihydrate and then use that for titration. And that's much more reliable. And so when we get our Erlenmeyer flask, rather than putting a solution in here, we're going to put some, this is a white solid, we're just going to put some oxalic acid dihydrate in here, and how much? 0.750 grams of oxalic acid dihydrate. So 0.750 grams. H2C2O4.2H2O solid. So from this, we know, or at least we can calculate quite accurately how many moles of oxalic acid we have in there. And then we're going to add water to this. And when we add water, what that's going to do is it's going to pull apart the crystal lattice and dissolve the oxalic acid molecules in water. Oxalic acid is soluble in water because it's light dissolved light. Oxalic acid has hydrogen bonding interactions. Water has hydrogen bonding interactions. We both have hydrogen bonding interactions. And so when I add water to this, I'm going to get oxalic acid aqueous. But am I going to get oxalic acid dihydrate aqueous? And it turns out no. What's going to happen is these waters are like imprisoned in the crystal. When I dissolve the crystal, it breaks the crystal apart and it frees up the water. And so when the water gets freed, it can readily join the other water molecules in solution. And so what I end up with is I just end up with oxalic acid aqueous. And so when I dissolve the lattice again, the lattice breaks apart, freeing up the water, and then I just have my oxalic acid aqueous. And that oxalic acid aqueous, I can just titrate. Depending on how much water, we can figure out the concentration, but we don't care what the concentration of oxalic acid is in this particular problem. In this particular problem, we care about what the concentration of the sodium hydroxide used is. So student dissolves 0.750 grams of oxalic acid dihydrate in water and titrates the resulting solution with a solution of sodium hydroxide at unknown concentration. And so over here, we're going to have sodium hydroxide aqueous. But the molarity is unknown. We don't know what that molarity is. But they did use 28.0 milliliters for titration. All right, this is a problem because how much are burettes? Do you know the cost of a burette? The burette's $200. So if you pay $200, how much precision do you want? A lot. This is not enough precision. So I think this is why people screw up in Chem 1A. Because in Chem 4, it's always 368. In Chem 1A, it's always 468. And so, we should be reading the burette to the nearest 100. And so they should have been read like 28.00 milliliters. Not 28.0, so this is really bad. But they're trying to make your life simpler, but it makes things more complicated later on. And so what we're going to do is we're going to use a primary standard to titrate the sodium hydroxide. When we titrate the sodium hydroxide, what we're going to be doing is this. We're going to be standardizing the sodium hydroxide solution. When we standardize the sodium hydroxide solution, we figure out the molarity as accurately and as precisely as possible. And so in day one of the Chem 1A titration, we use oxalic acid dihydrate to standardize sodium hydroxide solution. Once we standardize the sodium hydroxide solution, then that's our secondary standard. We're going to use that standard to titrate an unknown acid and try to identify what that unknown acid is. That's in Chem 1A. But that's day two. We'll stick with day one here. And so the molarity of the sodium hydroxide is what we're after. The molarity of sodium hydroxide is the moles of sodium hydroxide contained in some number of liters of sodium hydroxide solution. So how many moles of pure sodium hydroxide are contained in liters of sodium hydroxide solution? Well, we have 20.0 milliliters of sodium hydroxide solution that was used. And so we can convert that to liters. And so this is going to be moles of sodium hydroxide per 0.0280 liters, so 0.0280 liters of sodium hydroxide solution. So what we're going to do is we're going to figure out the moles of sodium hydroxide from stoichiometry. Yeah. So the first thing is we need to know what is the molar mass of oxalic acid dihydrate. All right, so some of these, actually, all of these elements I have memorized. For example, hydrogen is 101. So how many hydrogens do I have altogether?
6.
6. So if I have 6 hydrogens, that's 6.06. 6 times 101. I have how many carbons? 2 carbons. I know carbon is 1201. So 1201 times 2 is 2402. How many oxygens do I have? Altogether. 6 oxygens. 2 oxygens, well, 1 oxygen is 16, 2 oxygens is 32, so 2 times 3 was a 6, so 32 times 3 would be 96. It will be 96. So some of these, it's helpful to have memorized because it just speeds things up, the calculation. So if you go to organic chemistry, you definitely have these memorized because you don't want to waste a lot of time doing a molar mass calculation. You want to be able to do molar mass calculations quickly so you can do the other stuff. You have at least have more time for the other stuff. Anyway, this is going to be 26.08. So we'll know how many moles of acid. Once we know how many moles of acid, then we'll know how many moles of base. And we can do this later on based on the equation. It's a diprotic acid. So for every oxalic acid, I'll need 2 sodium hydroxides because I have 2 acidic hydrogens. And that's going to make 2 waters plus sodium oxalate. Okay. So it's a 1 to 2 mole ratio, 2 moles of base for every mole of acid. And so we'll go ahead and do the calculation here. It's going to be 0.750 grams. So 0.750 grams of oxalic acid. But this is oxalic acid dihydrate, solid. The water molecules are stuck in the lattice. And 1 mole of this dihydrate, and so H2C2O4.2H2O, weighs 126.08 grams. And so the grams of oxalic acid dihydrate cancel. And then for every mole of this solid that I dissolve in water, I will end up with 1 mole of oxalic acid molecules, and 2 waters then are free from the lattice. So I end up with 1 mole of oxalic acid molecules that are freed up when I dissolve 1 mole of oxalic acid dihydrate. That just comes from the chemical formula. And so for every one of those, I get one of these. And then I'll need 2 moles of sodium hydroxide to neutralize 1 mole of oxalic acid. And this will give us the moles of sodium hydroxide here. So let's go ahead and calculate the moles of sodium hydroxide. Actually, 0.75 divided by 126.08 times 2. 0.01189 moles of sodium hydroxide are contained in 0.0280 liters. And so I'll take the moles divided by 0.028. I'm going to get 0.4249 molar. So when I standardize the sodium hydroxide, I want to know as accurately and precisely what that is. So I'm only allowed 3 sig figs. And so the concentration of my sodium hydroxide is going to be 0.425 molar. The concentration of oxalic acid I didn't care about because I know how many moles there were, and that's all what I need. I need to know how many moles. Whereas for your HCl titration, you needed to know the concentration of HCl because you use that solution. Here we just use the pure acid, the dihydrate. So this gives us the molarity of the sodium hydroxide. All right, where did I leave off last time? I was in chapter 18 or still in chapter 17? 18? Collision theory? Okay. Okay. So in chapter 17, let's see. We have the 3 definitions for acid bases, right? Arrhenius, acids H plus, bases OH minus. Bronsted, acid is a proton donor, base proton acceptor. Lewis, acid is an electron pair acceptor, base is electron pair donor. And then for Bronsted, we have the conjugates, pairs. For Bronsted, we have the acid chart, strength chart. For Bronsted, we have predicting acid-base reactions using the chart method or the zigzag method. There's a comparison with redox. We don't need to compare, they're different. And then we have the water equilibrium. I talked about that, right? KW. Yeah. All right. So we didn't really do any calculations then. But we did know that pure water has a pH of what? 7. And if the pH is below 7, is that acidic or basic? Is that acidic? And if the pH is above 7, and the general range for pH ranges from pHs generally range from 0 to 14, but it's not really 0 to 14. The range is a little bit wider, right? The lowest pHs found, you know what the lowest pH measured was? Not 0. Did I talk about Iron Mountain? It goes negative. The lowest pH measured is in California. I didn't talk about this? Oh, I forgot. Excuse me. These are some of the lowest pHs ever measured from Iron Mountain, California. What was it? Extremely acidic mine water with pH values as low as negative 3.6. That's crazy low pH. It's crazy low pH, and therefore Iron Mountain is classified as a Superfund site near Redding, California. It's an environmental hazard. They call it the Iron Mountain disaster. Tailings. So anyway, the two dominant sources of extreme acidity in natural waters are magmatic gases, or these volcanic gases, that contribute HCl, HF, and H2SO4 from oxidation of H2S and SO2 to vent fuel crater with oxygen. Well, don't go swimming in Iron Mountain, California. Anyway, let's go back. The highest pHs. Can you have pHs higher than 14? Yeah, the same. pH is high. The general range from 0 to 14 behaves nicely. All the equations, all the calculations that are shown in the chapter work when the pH is within the range of 0 to 14. When you go outside the range of 0 to 14, let's say you go to pHs that are negative and pH is greater than 14, then we have to use some special equations for that. The special equations are for these higher concentration solutions. So the equations that are in that chapter don't work so well. And so this is why when you do pH calculations, everything's between 0 and 14. There's nothing lower than 0, nothing greater than 14. Because those calculations would require more advanced equations than what you're given. But between 0 and 14, they work well, so we use them between 0 and 14. Chapter 18 is strangely organized. I don't like the way chapter 18 is organized. So what some books do is they divide it, they split it into two separate chapters. So our chapter 18 is two chapters, which is okay, except I think in your book is the number is going to be different than in mine. But in my book here, 18, 2, 3, and 4 deal with kinetics. And kinetics talks about the speed of the reaction, how fast it occurs. 18.1 and then 18.5 through the end, chapter deals with equilibrium. Mine would be 18.12. In your book, I think these are all offset one. This deals with equilibrium. These are two different things that we look at. Equilibrium is often termed thermodynamics. And so in most books, they separate the kinetics from the thermodynamics because we ask two different things here. They're not the same thing. For kinetics, there's the speed of the reaction. The speed of the reaction we usually look at in terms of the reaction profile diagram. And so we're interested in how fast two water molecules react. then we need to know how they react. Well, how they react is they collide with one another. And a collision should have two things in order for reaction to take place. One, they have to collide with enough energy to break the bonds. And two, they have to collide with what? Did I talk about this? I don't remember. The correct orientation. Right. And so in this case, we need the oxygen to collide with the hydrogen. We don't want hydrogen to collide with hydrogen, and we don't want oxygen to collide with oxygen. It has to be the oxygen has to collide with the hydrogen. If that's the case, then let's say we're at this energy. We have to have enough energy to break and form a bond. And so the energy goes up. And so this is kind of the progress of the reaction. Boom, there's a collision. And at the top of the peak here is something called the transition state. The transition state is a state that's transitioning from reactant to product. So we have a bond that's forming and then a bond that's breaking here. And so here, on the one hand, this new bond's forming and this old bond's breaking. And that's going to be at the peak of the energy. And then it's going to drop down in energy to the product. The products are still higher in energy. This is not a favorable reaction. This is what we call an uphill reaction because we're going from lower energy to higher energy. And what we're going to form are the products here. The products are going to be H3O plus, hydronium, and OH minus, hydroxide. Hydronium hydroxide. This is not a favorable reaction because a favorable reaction would be going, this is an acid-base reaction. It'd be going from stronger, less stable, to weaker, more stable. Here we're going from weaker to stronger. The weaker is more stable, and so this is the proton acceptor. Proton acceptor is the acid, or proton acceptor is the base. Proton acceptor. In Bronsted. This is Bronsted acid-base reaction. Bronsted acid-base reactions transfer protons. And so Bronsted acids are proton acceptors or proton donors? Bronsted acids.
Donor.
Yeah. And so the first water would be a acid or a base?
It's the base of acceptance.
Yes. So this would be the base. This would be the acid. Water can go either way. So this water is acting as the base. This is the acid. If something can go either way, we don't call it an acid. We don't call it base. We call it, there's another name for something that can act both as an acid and a base. What's that name? Starts with an A. Kind of. But we don't call it ambiguous. We call it something else. Ambiguous is AM, and AM is correct. AM, not ambiguous, but I didn't talk about this. Amphoteric substances can act either as an acid or base, and they'll occur on both sides of the acid-base chart. And so water is amphoteric. It can go either way. Hydronium is not amphoteric. Hydronium can only go one way. It's the acid. Hydroxide is actually amphoteric. It's weird. Hydroxide is amphoteric because it could either gain a proton or it could lose a proton. But in this case, it's not amphoteric. Here, in this case, hydronium, because going backwards, loses the proton, therefore hydroxide must be the base. And so its role is going to be identified by the reaction if we go backwards here. And so what we're doing is we're going from weaker base to a stronger base. Hydroxide is a much stronger base. And then we're going from a weaker acid to a much stronger acid. Hydronium is a strong acid. So this is not favorable. This is thermodynamics. Thermodynamics is this. This is uphill. And so this is the thermodynamics part. Thermodynamics says this is uphill. Thermodynamics part says, well, this is uphill. And therefore, is anybody going to make it up this hill? Let's say you have a whole bunch of bicyclists down at the bottom of the hill. Can any of the bicyclists make it to the top of the hill? Well, it depends. You know, how steep and how long of a hill is that? The steeper and the longer the hill is, the less chance there is of a bicyclist making it to the top. But we can see, because not all the bicyclists are going to be the same. You know, are all the water molecules at the bottom of the hill the same? Even though they're all at the same temperature. Yeah, if this were at 25 degrees C, we know that not all of those are the same. In fact, we have something that describes the population in terms of kinetic energy. And it's a curve or distribution. Do you recall what that's called? Starts with an M. So at 25 degrees C, some of the population will have this energy, some will have this energy. It just describes that. It looks like this. So when we look at the population of water molecules at 25 degrees C, not all of them have the same energy. There's going to be a distribution of energies. It's a skewed curve like that, in which we plot the kinetic energy on the x-axis. So high population of molecules with this kinetic energy, lower population of water molecules with this, and low time. This is the population on the y. Yeah. This is the Maxwell-Boltzmann distribution. For water at 25 degrees C, let's say my population were about 1 billion water molecules. If I had about 1 billion water molecules, so I have 1 billion bicyclists here, about how many bicyclists can make it all the way to the top of this hill out of that billion? Isn't it like 4? About 4, yeah. Because that hill is a very steep hill to climb. And so this is the energy cutoff here to climb that hill. Actually, to climb that hill, it has to climb a little higher. It has to go here. It has to make it all the way here, but we lose energy coming down here. And so net, this is the amount of energy that's gained. Does that make sense? Climb all the way up here, and then lose some energy coming down. And so this is the amount. And so about 4 out of 1 billion. Normally, do you worry about that? If it's only 4 out of 1 billion, we don't normally worry about that so much. And so this is the second part. Part 2 of chapter 18 deals with equilibrium. This is called an equilibrium because are these 4 going to stay there No, they're gonna probably get bored. They're probably gonna want to go back down the hill. But then, if 4 of them go back down the hill, then another 4 are gonna make it back up the hill. And eventually, we're gonna have a situation where we have a dynamic equilibrium. A dynamic equilibrium means the number of bicyclists going up the hill is equal to the number of bicyclists going down the hill, and therefore, the population is stable. That is, we'll have a billion down here and 4 up there. And then we'll have a dynamic equilibrium. Equilibrium means the population doesn't change. In this dynamic equilibrium, it tells us nothing about how fast the reaction happens. In other words, for those first 4 to make it to the top, let's say 100% of the population is at the bottom of the hill. How long is it going to take for the first 4 to make it to the top of the hill? That's kinetics. Kinetics is how long is that going to take? For some reactions, it takes a very long time. For other reactions, it's very fast. And so this is the equilibrium part. The kinetics part is how long does it take? How long depends on this, because we have to get to this transition state here. So how long depends on the activation energy. The activation energy is the energy required in the collision to have a successful reaction. How long is going to depend on the orientation. Actually, there's going to be more than 4 that have enough energy. But the collision has to have the correct orientation. And so some of these that have enough energy just don't have the right orientation. It's going to depend on the temperature. Because the higher the temperature, the greater the population of higher energy molecules. The lower the temperature, the lower the population. So in kinetics, we ask how long this takes. How long this takes depends on the climb. How high is that climb? The easier the climb, the lower the activation energy. And so this is an easier climb. This is an even easier climb. The lower the activation energy, the greater the population. So if I have a billion, maybe 1/3 of those can make it to the top of the hill. The higher the activation, the fewer the population. So the activation energy is going to play an important role in how fast. So the lower the activation energy, the faster. The higher the activation energy, the slower. The activation energy depends on what we call the mechanism or the path. So in this case, the path is the oxygen has to collide with the hydrogen. Sometimes what we can do is we can provide an alternate path. And that alternate path means maybe we don't climb all the way to the top and drop down. Maybe we can go around the side. If we can go around the side, that's going to lower the barrier. So rather than go up and over the mountain, we go around the mountain. Going around the mountain, we could use a catalyst. What a catalyst does is it might allow us to go around the mountain rather than over the mountain. If we can go around the mountain, then the activation energy is going to be a lot lower. And so what happens with a catalyst is I have an alternate hill to climb, and that alternate hill is smaller. And And so if I have a catalyst in there, it's going to look like this. So I already talked about this, right? Orientation and energy. So this is the activation barrier that we have to climb over. And it depends on how tall it is. Then that's going to dictate what population can make it over. In this case, this ball had enough energy, but this ball didn't have enough energy. It only made it up to here and then rolled back down. So that was unsuccessful. That hill shown here. Overall, this is a downhill reaction. So we expect everybody to make it down here. Everybody should make it down here. But it's not going to happen so quickly, because in order to react, there has to be a collision. And in order for the collision to lead to product, there has to be bond breakage and bond formation. And so initially, there's going to be a little hump here that's going to slow things down. And so this hump means it doesn't go straight downhill like a waterfall. We're going to have to react and then drop down here. And so this is a downhill reaction, and we expect most of the population to make it down here. This is an uphill reaction, where we expect most of the population to stay down here. And so in this case, most of the population will be here. And it's not going to be super fast, because what has to happen is it has to go over this initial hump to make it downhill. Overall, when we look at delta E is going to be negative. So we climb this, but we're going to get that energy back here, and then we're going to get more energy here. Now, in equilibrium reactions, what happens is everybody should make it down. So eventually everybody makes it down here. But is the entire population the same? No. Maybe some bicyclists might get bored. They made it down the hill, no big deal. So if they get bored, they might try to climb back up. Now, depending on the Maxwell-Boltzmann distribution, there could be enough population to climb back up. If they can climb back up, then we end up here with some reactant. And eventually what we'll hit is we'll hit a state of dynamic equilibrium, because as let's say 2 or 3 or 4 or 5 climb back uphill, then those can go back down. But then they're going to be replaced. And so we'll hit the state of dynamic equilibrium where some will climb back up, and then we'll reach a state where the number coming downhill and the number going uphill are equal. And so we have this state of dynamic equilibrium. And so in equilibrium reactions, what we have is a state where we have a partial reaction. And so here we have partial reaction. Over here, even though we should have full reaction here, climbing back up the hill and going backwards is not impossible. So in this case, if that's the case, then 100% of the population is in product. There's going to be some percentage up here. Does that make sense? And so that's a case where we have partial reaction, or it doesn't make sense. Doesn't make sense?
Even for reactions that are in equilibrium, some combustion reactions.
Yes, right. And so far in Chem 4, we look at complete reaction or no reaction. So for example, like combustion reaction, methane, oxygen. These are all gases except for water. This one is very far downhill. And so we have methane plus 2 oxygens way up here, going down to CO2 plus 2 waters way down here. So the entire population can make it down the hill. Once the population makes it down the hill, this hill is too steep and too long for these to go back up the hill. And so this is what we call complete reaction. Complete reaction depends on what the limiting reagent is. The limiting reagent is going to be completely consumed in the reaction. And so everybody makes it downhill. It doesn't happen so fast. So for example, when I have methane bleed into the room, do I have instant reaction here? No, it's kind of slow at room temperature. How can I speed it up? I can speed it up by heating it up. If I heat this up with a match or a hot piece of metal, then the reaction is going to happen rapidly. And so I need something to get it hot over the hump. And so that's the activation barrier here. And so this reaction happens slowly because I got to go over this initial hump. But I can really speed it up if I can get these to collide with more energy. That is by increasing the temperature. And then it'll drop down over here. But the thermodynamics part is this. This is pretty much a one-way reaction. And the yield is going to be a complete reaction depending on what the limiting reagent is. So if methane's the limiting reagent, we're going to use up all of it. If oxygen is the limiting reagent, we'll use all of it. And we'll get complete reaction. The reaction is going to be a little bit slow initially because of this activation hump. Whereas there are other reactions that are not quite the same, like this one here. Let's find another one. I don't want to do too complicated a reaction. I'm going to find a simple one. The one that they showed over here is kind of complicated one. This one we expect to do the same thing. What we expect is all hydrogen and iodine to go downhill to make hydrogen iodide gas. Actually, iodine in this case is a gas. Iodine is normally a solid, so this must be a higher temperature. But it turns out that we only get partial reaction here. Because what can happen is some of these HIs can go back up the hill. In fact, not all of them will stay down here. And so what we end up with is a case of partial reaction. Some go back uphill. This one, the kinetics part is it has to get over this hump. So initially it's going to be kind of slow, like this. The thermodynamics part is we're going to have a mix. And so when we have partial reaction there, how do you do the stoichiometry? What we do for partial reactions is this. We use equilibrium stoichiometry. When we have complete reaction, we just use regular stoichiometry. So let me give you another example of a partial reaction. Weak acids. Weak acids are weak electrolytes. Weak electrolytes partially ionize or partially hydrolyze in water. Right? So if I have a weak acid, do you expect it to be 100% ionized in water? No, we expect partial. When we do equilibrium calculations, we want to know how much. And so sometimes I'll write the number. Remember this number? 99.9% this, 0.1% that. Where did I get that number from? Where I got that number from is by doing equilibrium stoichiometry. Equilibrium stoichiometry is what we use for partial reactions because we don't have complete reaction here. Some of these are going to go backwards and populate this, so both are populated. And so at the end of this, when I hit equilibrium, when there's no more change, I have both reactant and product present. Does that make sense? And the same thing here, it could be uphill. And you think, well, if it's uphill, nobody's going to go uphill. But that's not the case. It depends on how far uphill it is. If it's too far uphill, then pretty much nobody can make it. And so if it's too steep and too long, I have no driving force. It's not going to make it. But what if it didn't have to climb all the way up here? What if it was a much smaller hill? If it's a much smaller hill, then most of the population is going to be down at the bottom of the hill. But there's going to be some aggressive ones that make it to the top. And so here we have partial reaction. Again. So if we have partial reaction, how many make it to the top of the hill? That's equilibrium stoichiometry, part 2 of this chapter. How fast? Well, how fast it occurs, there has to be an initial transition state. The initial transition state is this big hump. To get over that hump, well, to get over that hump, we look at how big is that hump? The activation energy. 1. 2, is there a catalyst, that could lower it? If not, then 3, temperature. Increasing temperature will get it over the hump faster. So reactions happen faster at higher temperature. That's kinetics. Reactions happen faster at higher temperature because the population increases. The higher energy population increases. So the blue curve shows the Maxwell-Boltzmann distribution at 25 degrees C. The red curve shows it at 75. At 75, it shifts the population to higher energy. And so at 75 degrees C, there are a lot more molecules that have enough energy to make it over the hump. The hump is the EA, the activation energy, which is the minimum energy part of the reaction. In this case, 260 kilojoules. The temperature will have an effect. The size of the hump will have it. So with the catalyst you can kind of go around the hill rather than going over the hill. So the red one shows no catalyst. With the catalyst, it provides an alternate path for reaction, shown here. There's 2 humps here in this case. But it's a lower energy, even though there are 2 humps here, it's much lower energy. If it's a much lower energy, then the population is going to be much greater. And so catalyzed reactions go a lot faster than uncatalyzed reactions. Interestingly, the catalyst isn't consumed in the reaction. Well, the catalyst may be consumed initially, but it's regenerated at the end. And so catalyst can be used over and over again. So the things that impact the rate And this is collision theory. Is temperature primarily and catalyst. Some reactions we don't have suitable catalysts for. So here's a catalytic decomposition of hydrogen peroxide, which happens very fast. There are lots of examples of catalytic reactions. Another thing that impacts the rate of the reaction is changing the concentration, which essentially changes the population. And so if I increase the concentration, which is increasing the population for a given volume, then I'm going to have more molecules. The more molecules I have reacting, the faster the reaction is going to take place. And so another way is that we can burn things in air. Air is 20% oxygen, but we can burn things in pure oxygen. Pure oxygen is 100% oxygen. And so things are going to be burned much more intensely in pure oxygen than in air. And so this is just showing this. This is a piece of wood burning in pure oxygen versus a piece of wood burning in air. And you can see the wood burning in the oxygen, pure oxygen, is much more intense, more violent. And it's going to happen faster. And this is going to be more collisions per unit volume. All right, so that's the speed. The speed of the reaction is going to depend on this activation barrier here, the hum. And so the kinetics part is this gas part. The thermodynamics or the equilibrium part is the solid line part here. Is it downhill overall, uphill overall? What is it? And in the equilibrium stoichiometry, we want to know, what is the population? So here it's pretty much 100% reaction. That's what we predict using equilibrium stoichiometry, so that we use regular stoichiometry. But in other types of reactions, we only have partial reaction. We only have partial reaction because not all the population stays here as product. Some will revert back out. And then the same thing, not all the population stays here as reactant. There's going to be a small slice of the population that can make it up. And then we'll reach a state of dynamic equilibrium. The state of dynamic equilibrium is, there's going to be a stable population, at the top of the hill and at the bottom of the hill. But it's dynamic because, they're going both ways. So this graph here is showing the approach to equilibrium. F stands for forward reaction, R stands for reverse. So initially we'll only have forward reaction. So initially we only have forward reaction, goes over this hump, makes it down here. But as the population of the product grows and gets bigger and bigger, as this population gets bigger and bigger, then some of them will go back up. That's shown in blue. So initially we only have forward, but as the population of the product increases, then we'll have the reverse. Eventually we'll hit a point where, let's say 10 make it down and 1 makes it back up. But eventually we'll get a point where 10 make it down and 10 make it back up. And that means the forward rate and reverse rate are equal. And so this black line shows the achievement of dynamic equilibrium. The dynamic equilibrium is when the rate of the forward is equal to the rate of the reverse. Here we're achieving equilibrium. This graph you don't have to know at all for the test. So this is just introduction to this. Here. Le Chatelaise is once we establish equilibrium. I'm going to skip Le Chatelaise for now because it's out of place. We're talking about this equilibrium stuff right now. Le Chatelaise, they spend a lot of time in this chapter talking about Le Chatelaise effect. But that happens after equilibrium has been established. So what we want to know is what is the population here? You know, how much makes it back up the hill? Or how much makes it up the hill? We want to know what that is. And so normally the way that's characterized for these are equilibrium reactions. Equilibrium reactions are mainly partial reactions. They're partial reactions because they end up going both ways. Both downhill and uphill. And so the thing that we use to characterize this is K, the equilibrium constant. K is essentially the ratio of the product. It's a little bit more complicated than this, over reactant. And so it's the product to reactant ratio. So how much of the population is product? How much of the population is reactant? If it's 100% product, yeah, that would be a complete reaction. And K would approach infinity because you'd have zero reactant. If you have no product, all reactant, that is 0% reaction, K would be zero. And so if K approaches infinity, we have complete reaction. But it doesn't have to go all the way to infinity. If it's a huge number, then essentially it's complete reaction. You know, huge number, pretty much all product. If it's a tiny number, it's pretty much all reactant. And so we use K to tell us what that is. So for example, this, H2O plus H2O liquid, most of the population is going to be down the hill here. Because this is a very long and steep hill decline. It's a very long and steep hill decline because hydronium and hydroxide are very strong acids and bases. And so they're very reactive. And so when I look at this reaction, H2O liquid plus H2O liquid produces hydronium and hydroxide. I look at the K value. This K is a very important K. A lot of people will memorize the K value for this. And they call it KW. KW is 1.0 times 10 to the minus 14 at 25 degrees C, room temperature. And so what that means is I have like this. I have 1 part product. What would it actually? No. I'd have 10 to the minus 14 parts product, 1 part reactant, or flip it around. I'll have 10 to the 14. So if this were a population, it would be like 10 to the 14 down here and 1 up there. Does that make sense? Something like that. It's a little bit more complicated than that. This is the equilibrium constant for this water reaction here. And this gives us the ratio. And so this is tiny. This tiny tells us it's mostly reactant and very little product. So how do we do this? Let me show you an example of an equilibrium calculation. You don't have to do this. I would do this if we talked about this in Chem 1A. If equilibrium calculations were the subject of Chem 1A, I'd probably talk about it. But it's a subject of Chem 1B. And I figured that, most people will forget it because there's a gap. And so I normally have to start from the beginning in Chem 1B anyway. The equilibrium constant here is equal to the hydronium ion concentration times the hydroxide ion concentration. But where's the water? Hydronium and hydroxide are the products. The reactants are water, but water is a pure liquid. And so pure liquids and solids are not shown, or they're kind of omitted. They're not really omitted. From the equation, I'll just say not shown. Let me put that in quotation. This is a little bit more tricky. So the water is not, the water's there, it's one. This is the hydronium concentration of equilibrium. Times the hydroxide concentration of equilibrium. And so an example of an equilibrium calculation involves ICE. And so what I have is H2O liquid plus H2O liquid. This is going to go to hydronium and hydroxide. And I set up what's called an ICE table. ICE stands for initial change equilibrium. Equilibrium, I'll just abbreviate EQ. Pure liquids are omitted, or not shown like that. And so let's say initially I have 0 molar and 0 molar. And so the way I visualize this is initially my entire population is here at the bottom of the hill. That's my entire population. But not everybody's going to stay at the bottom of the hill, right? Because of the Maxwell-Boltzmann distribution. There's going to be a very small population that may have enough energy to make it to the top. What is that population? I don't know what that population is. And therefore, I'm going to call it plus X. X are going to be the highly energetic bicyclists that are going to make it to the top of this hill. Plus X and plus X. You see that? And so, some of these plus X will make it to the top. And therefore, when I'm done with this, that is, once I reach a state of dynamic equilibrium where the ones coming up the hill are equal to the ones going down the hill, then I'll have a stable population at the top of the hill. That stable population is going to be called X. And so, an equilibrium calculation is going to be like this. Kw is equal to the hydronium concentration times the hydroxide ion concentration at equilibrium. And this is equal to a constant, 1.0 times 10 to the minus 14. This is a constant. This is called the equilibrium constant at this temperature. And therefore, the hydronium ion concentration at equilibrium is X, whatever that population is. And the hydroxide ion concentration is 1-to-1, is also X. And this is equal to 1.0 times 10 to the minus 14. And therefore, X squared is equal to 1.0 times 10 to the minus 14. And therefore, X is equal to the square root of that, which is 1.0 times 10 to the minus 7. And so the hydronium ion concentration is 1.0 times 10 to the minus 7 molar, and the hydroxide ion concentration is 1.0 times 10 to the minus 7 molar. Do you know what the pH is? If I have 10 to the minus 7 molar hydronium, the pH is going to be 7. And so this gives us our pH equal to 7.00. And so I can figure out what the population is. Up here, the population is very small because I know what K is. The Ks are usually given in a table, or sometimes you measure them. The K values you can find for a lot of equilibrium reactions in tables. And we use that to determine what the populations are on both the bottom and the top of the hill. Does that make sense? So that's what equilibrium is all about. Equilibrium is about figuring out this population. Kinetics is about how fast. So I'm completely ignoring kinetics. I don't care how fast or how slow this occurs. I just want to know what the population is going to be after I give enough time for this to happen. So what you need to know is that when we're dealing with equilibrium, we have this two-way thing happening. When we're dealing with standard stoichiometry, it's one way. It's not two-way. And so all the stoichiometry problems we did up to now were one way, complete. You know, everybody's going to make it to the bottom of the hill because there's a driving force. And if it's uphill, there's no driving force, therefore there'd be no reaction. So the first thing is the equilibrium constant expression. This is just going to be an example. Take a look at some examples here. You don't have to do these. But you should know that the equilibrium constant tells us the ratio of product over reactant. But it's a little bit more complicated. And so these are just examples where it's a little bit more complicated. So for example, if I look at this first reaction, 41, carbon monoxide gas plus H2O gas yields carbon dioxide gas plus hydrogen gas. This is one way of making hydrogen. This is called the water gas shift reaction. And this is an important reaction for making hydrogen using steam and carbon monoxide. This is partial reaction. This is not a complete reaction. You know, in a typical stoichiometry calculation, we look which one's the limiting reagent. The limiting reagent will be completely consumed. But in this particular reaction, what happens is both sides. The top of the hill and the bottom of the hill are populated. And so it's a partial reaction. If it's a partial reaction, then what we want to know is we want to know the ratio. And in this case, the ratio is just going to be the carbon dioxide concentration times the hydrogen gas concentration divided by the carbon monoxide concentration and the H2O gas. H2O is normally liquid, so I'm going to write gas in this case. H2O gas concentration. Because if H2O is liquid, then we omit it or ignore it or don't show it. You know? And so this is the product to reactant ratio. This. And this is going to be a constant, you know, at a given temperature. We can look up what that constant is. If it's a big number, then we expect lots of product. If it's a tiny number, we don't expect much product. This number is not so big. You know, so we get partial reaction. And so we wouldn't expect 100% yield in this. We're going to expect maybe a much lower yield, depending on the conditions. Normally, when we get lower percentage yields, the lower percentage yields are from losing. So you might not get 100% yield because you lost some of the crystals. You know, you didn't want to hassle with scraping every single crystal off the piece of paper, filter paper, or some of the crystals got stuck on the inside of the test tube. You didn't want to scrape every last bit out. And so normally we get lower than 100% yield because of losses. Those losses could be prevented in theory, and you could get 100% yield. But these partial reactions like this, it's impossible to get 100% yield. You can't keep the population at the bottom of the hill because some are going to make it back up to the top. Does that make sense? And therefore, a lot of these are going to, you expect these to have lower than 100% yield. All right, so anyway, let's stop here. I'll take a break and then. Okay, we'll get started again here. Were there any questions earlier? No. All right, so the equilibrium constant, K, is going to tell us the ratio of product to reactant. So in this particular case, I don't know what it is. You know, maybe it's 80% product, 20% reactant, something like that. But K will tell us that. And that number we look up in a table. We solve for it. Once this is established, the correct ratio, then it's said to be in a state of dynamic equilibrium. The dynamic equilibrium means the population is stable, it's not going to change. But it's dynamic because it's going both uphill and downhill. And so the number going uphill is equal to the number going downhill. I don't know which one's uphill and downhill in this particular reaction. It's a bit trickier here. There are ways we could determine it. But once this is established a stable population at the top and the bottom of the hill, we can perturb it. That is, you know, perturbing just means upsetting that population equilibrium. We can upset it by changing the concentrations. So, for example, if we increase the concentration of a product or the products, you know, then we get too much. It becomes too top heavy. If it becomes too top heavy, it has to shift to the left to reestablish an equilibrium. Or if we increase the product of a reactant or both reactants, it becomes too bottom heavy. Instead of shifting to the left. It's Le Chalet's principle. Le Chalet looks at the shifts that occur when a system's been perturbed from equilibrium. But the equilibrium is going to be defined by the equilibrium constant. Let's take a look at number 42 here next as an example of equilibrium constant. We have ammonium hydrogen sulfide, ammonium bisulfide, solid, going to ammonia gas and H2S gas. So ammonia gas and hydrogen sulfide gas. And so this is going to achieve some state of dynamic equilibrium. It's not going to be 100% reaction. It's going to be some partial reaction. And that ratio in population is what we want to know. And it's going to be K. K is going to equal the ammonia concentration, at equilibrium times the H2S concentration at equilibrium. Now, the ammonium hydrogen sulfide, or ammonium bisulfide, is solid. And so pure solids are just one. And so those are emitted. So there's nothing in the reactants shown here. This is like for water, the pure liquid. And so solids and liquids do not appear. So there's a solid here. There's a liquid here. That's not going to appear. Liquid here. That's not going to appear. Some of these are a bit more tricky. For example, zinc phosphate. If I look at zinc phosphate, ZN3PO4, that's a solid. So solids aren't going to appear in our constant or in the ice table. This is going to yield 3 zincs plus 2 phosphates. Now, it's product of a reactant. In this case, if we look at the coefficients here, what do we do with those? And so it's going to be the product concentration, Z2 plus, from the phosphate. But what we do with the coefficients and equilibrium constants is we use those as powers. And so the 3 here is going to show up in our K as a Q. And so it's the zinc ion concentration Q. And the phosphate will be squared because of the 2 here. Now this is a pure solid, so that's going to be down here as just 1. So 1 to any power is going to be just 1. And so it's the product to reactant ratio, but the product to reactant ratio is a little bit more complicated than just products or reactants. These, you aren't going to have to do any of these. I decided I'm going to just omit the equilibrium constant. It's not hard to do. But, we get the expression. You aren't doing any calculations. If we're doing calculations, then yeah, I do these. But you don't have to do any equilibrium calculations. What you should know is the significance of K. The significance of K is it's the product to reactant ratio. So let's take a look at this particular reaction here in number 53. In number 53, we have the reaction one silver ion plus 2 cyanide gives this. This is a Lewis acid-base reaction. Silver ion is an electron pair acceptor. Cyanide is electron pair donor. So silver ion is the acid, Lewis acid. Cyanide is the Lewis base, and we form a Lewis acid-base atom. The name of this is dicyano argentate 1. This name you learn in Chem 1B. But anyway, this is a partial reaction. Well, maybe it's a partial. Look at the K value for this. K is equal to 5.6 times 10 to the 18. 10 to the 18 is what is that? A large number or a small number? Yeah, it's huge. This is a huge number. This huge number means it's practically all product or all reactant? Practically all product. In fact, if you have a number like 10 to the 18th, that's almost like 100% reaction. There's just a tiny, tiny bit. So 100% reaction, that's like, all this is going to just fall downhill. But maybe 1 might make it back up to the top. If this is 1 out of trillions, then is it really that significant? More than trillion. So. This one, though, if we look at this reaction, which is hypochlorous acid plus fluoride yields chloride and hydrofluoric acid. This is a Bronsted acid-base reaction. Hypochlorous acid is our proton donor. Fluoride is our proton acceptor. And so fluoride takes the proton from that, makes hypochlorite ion and hydrofluoric acid. When we look at K for this, it's 4.86 times 10 to the minus 5. 10 to the minus 5 means what? it's mostly product or mostly reactant? Mostly reactant. But, 10 to the minus 5 is not super small. That means we can expect some product in this case. It's not, and so there's at the top of the hill, which it's not such a terribly steep, well, it's still pretty big, 10 to the minus 5. If it were like 10 to the minus 1, then it wouldn't be. 10 to the minus 5, it's mostly, let's say, 10,000 parts reactant, 1 part product. But it's not crazy. And so in this case, we expect significant quantities at the top of the hill and at the bottom of the hill. But definitely biased towards the bottom of the hill here, the reactants at the bottom of the hill. Does that make sense? A certain equilibrium has a very small equilibrium constant. Very small means reactant biased or product biased? Reactant. And so mostly reactants. In which direction, forward or reverse, is the equilibrium favored? So it's going to be favored in the downhill direction, which would be forward or reverse? Reverse, right. It's mostly reactant. Reactants are going to be at the bottom of the hill. 56, acetic acid is a weak acid. Weak acids are weak electrolytes. Weak electrolytes, do they completely react or partially? They partially hydrolyze or ionize. And so it would look something like this. The reaction would be a Bronsted acid-base reaction. And I have my acetic acid here. In this case, it's hydrolyzing with water. Water would be the base. It's going to make hydronium and acetate. The thing is, we already know this is a weak acid. Weak acids are weak electrolytes. Weak electrolytes partially hydrolyze. So this is partial reaction. Partial reaction, we need to use K. We need to use equilibrium stoichiometry. Right? In other words, this is an equilibrium reaction. But that's not good enough. We want to know, okay, how much? What is the population? I told you before, we can figure out it's, what do they say? The equilibrium equation, will the equilibrium constant be large or small? So we expect K to be small. And in fact, I could look it up. Acetic acid is a very common acid. It's 1.8 times 10 to the minus 5. With a K of 1.8 times 10 to the minus 5, I can do the ice calculation. When I do the ice calculation, it comes out to greater than 99.9% and less than 0.1%. And so less than 0.1% of the population makes it to the top of the hill, but it's still significant because the pH for acetic acid is around 3 to 4 to 5, depending on the concentration. And so acetic acid yields significant hydronium to water, which increases the hydronium concentration, which will decrease the pH. Well, anyway, so what we have is 99.9% of the population's at the bottom of the hill, and then 0.1% of the population can make it to the top. Acetic acid is pretty weak. There are stronger acids. The stronger acids, like, for example, phosphoric acid. Phosphoric acid doesn't have as big of a hill. And so for phosphoric acid, it's more like 80% of the population's at the bottom of the hill and 20% at the top. So we get significantly more hydronium. And so it's not as big. So the stronger the acid, and then when we get to strong acids, it inverts. When we get to strong acids, K is going to be very large, but not infinite. And so when we get to strong acids like HCl plus H2O liquid, this goes downhill. Hydronium's weaker acid, chloride's a weaker base. So this is downhill. In fact, we say that strong acids are strong electrolytes. Strong electrolytes hydrolyze water completely. So we say that this is complete. And that means K is what we call very large. If K is very large, then that means that there's very little, or very few that can make it back up the hill. Does that make sense? In fact, if you take a look at this table here,
So when you say the K constant, it's not like pi, where something is just applied to an equation and you just use it. K constant is something you need to type of equation.
Right. So we have tables with K values. So if I look at HCl, what is the K value for HCl? It's very large, meaning that the strong acids completely hydrolyze, very large. Whereas if I go to weak acid like acetic acid here, acetic acid is 1.76 times 10 to the minus 5, kind of small. The stronger the acid, the bigger the K value gets. So if I go to oxalic acid, it's 5.9 times 10 to the minus 2. Well, 10 to the minus 2 is getting a lot bigger. And so oxalic acid has a much larger population at the top of the hill.
So it's not something that we can even calculate, we have to look at that.
You look it up, or you can calculate it. The way you know how we calculate the K values for acids? It's very easy to calculate the K value for acids because all we do is we get a pH meter. The pH meter is going to measure the pH. The pH is related to the hydronium concentration. And so we can determine, let's say I put in 0.1 molar acetic acid molecules in here. How many of those convert to hydronium? Well, if all of them converted to hydronium, then I get 0.1 molar hydronium. 0.1 molar hydronium has a pH of 1. But this only has a pH of about 4. So if this has a 0.1 molar has a pH of 4, then we can see what is the percent ionization, and then we can see what the population difference is. So we can easily calculate it. And so we don't have to get it off the table. We can determine it experimentally, but it's a hassle to determine it experimentally every time, especially for something like acetic acid, it's such a common acid. So what's much better is just to read it off the table rather than determine it, but it's easy to determine. So here, if you look here, they just tell us, calcium oxalate, what is the K value? 2.4 times 10 to the minus 9. The K value for silver nitride, 2 times 10 to the minus 8. So they give us the K value, and then we use that because that's going to tell us the population of the products, population of the reactants, and then we can use that to determine, things like what is the molarity, or what is the percent, or what is whatever. We can use those to do calculations. Those calculations are beyond the scope, so those are optional. And doing these, the significance of the K value, that's important. These are not, I'm not going to talk about these calculations. And then the K constant, that is determining what the K expression is, no, you don't need to do that. I just did some for examples. Except for Le Chatelier's principle. And so Le Chatelier's principle says this. If I increase the acetic acid concentration, that's going to upset the population balance. So if I increase the acetic acid concentration, I have too much reactant, and it's no longer properly balanced. So if it's no longer properly balanced, then there's going to be a shift. That is, there's going to be a net reaction. So if I increase the acetic acid molecule concentration, that's going to shift to the right and make monohydronium. Make monohydronium change the pH. And so this is Le Chatelier's principle. Le Chatelier's principle is going to be impacted by increasing or decreasing concentrations. It changes the ratio. Increasing or decreasing pressures, it's going to change the ratio. Changing the volume, that changes the concentrations, or changing the temperature. Changing the temperature actually changes K, because that's going to shift the Maxwell-Boltzmann distribution, and that's going to change the populations in that way. And so a lot of this, chapter 18, deals with Le Chatelier's principle. Le Chatelier's principle is there's a system at equilibrium, and you perturb it. When you perturb it, it screws up the ratio. And then what happens is there's a shift to try to get the correct balance again. It's not going to be the exact same concentrations, but it'll be the exact same ratio. And so let's look at Le Chatelier's principle 25. If the system, 2 sulfur dioxide plus an O2 yields 2 sulfur trioxide, this is a partial reaction. You know, one side's going to be favored. Depends on what the K is. I don't know which side's favored. Actually, I do know for this one. The products are favored. But they aren't favored so much that they can't go backwards and go up the hill. So there's going to be population of product and population of reactant. Okay. Once I establish the correct population, then it's in a state of dynamic equilibrium. But I can screw up that state of dynamic equilibrium. And so they say it is at equilibrium, and then you screw it up. You screw it up by decreasing the concentration of oxygen. So it was at equilibrium, now you screwed it up by decreasing O2. If you decrease the O2, that means the reactant, you don't have enough to maintain the balance. You lost some reactant. And therefore, what's going to happen is this is going to shift to the left. It shifts to the left to compensate. So if you lose reactant, it's going to shift to the left to make that balance again. Predict the direction in which the equilibrium will shift. It shifts to the left. Because removing O2 means we don't have enough reactant. Consider the following system at equilibrium. So this has reached a state of dynamic equilibrium when some chlorine is removed. So if we remove chlorine, we're removing reactant. If we remove reactant, that screws up the ratio. So which way is it going to shift? To the left to make up. We got to compensate for the lost chlorine by making more chlorine by shifting this to the left. If additional oxygen is pumped into the equilibrium, so this is at equilibrium, and then you pump in more oxygen. Now you have too much oxygen, too much reactant. It's going to shift to the right. We've got to get rid of some of that oxygen, so it shifts to the right. 28. Consider the following system in equilibrium. When some ammonia is removed. So if we remove product, ammonia, then we don't have enough product, and therefore it's going to shift it to the right. It's going to shift it to the right to make more ammonia, to compensate for the ammonia that was removed. Does that make sense? If the concentration of ammonia, so if we remove ammonia here, the concentration of ammonia is reduced, then we don't have enough product. Therefore, this has got to shift to the Well, if we remove ammonia, then we need to reestablish the balance by making more ammonia. So it's going to shift it to the right. Okay, so it shifts to the right. If we add ammonia, then it would shift it to the left because then we have too much ammonia. We have to shift it to the other way. Here's this equilibrium. Some COCl2 is added. If we add some COCl2, that's going to increase the reactant, which means it's going to shift it to the too much reactant means we've got to shift it to the right. It's going to be too much reactant because it was originally just the right amount. And so it shifts right. What will happen to the concentration of carbon monoxide? Well, if this shifts right, the carbon monoxide will increase. A container holding, this equilibrium is enlarged. So the impact of volume on equilibrium is, if you change the volume, it's going to favor the side with more moles of gas if you increase the volume, or it's going to favor the side with fewer moles of gas if you decrease the volume. So increasing volume favors more gas, decreasing volume favors less gas. So predict what's going to happen. So we're going to increase the volume. Therefore, it's going to favor this side, because this side has 4 plus 1, 5 moles of gas. This side has 1 plus 2, 3 moles of gas. So we're going to favor 5 moles of gas. If that's the case, increasing volume, and large volume is going to shift this to the left, making more of the reactant. Okay, if the volume of this is suddenly decreased, which side's favored? So the left side has 2 moles of gas, the right side has 2 plus 1, 3 moles of gas. So if we decrease the volume, the left side is favored, and therefore it's going to shift left. The right side has too much gas, so it's compressive. It'll shift left. What will happen to the moles of bromine? If this shifts left, then the moles of bromine will decrease. So if we look at this equilibrium, what happens to this equilibrium if we reduce volume? Which side is favored? That smaller volume. 33. The right side has how many moles of gas? So we have 1 mole of gas here plus 1, that's 2 moles of gas. The left side has how many moles of gas? The same. So the left side has 2 moles of gas, the right side has 2 moles of gas. Do you know what that means? Neither side's favored. And so what's going to happen is, if we reduce the volume or if we increase the volume, nothing happens, nothing changes, because both are equally favored. How about this one? The volume is suddenly increased. So if we increase the volume, which side's favored? The left side or the right side? Yeah, left side's favored. So this is going to shift left. So reaction runs reverse, shifts left. What will happen to the number of moles of oxygen? If it shifts left, the number of moles of oxygen will increase. Now this is temperature. Impact of temperature depends on if it's exothermic. If it's exothermic, heat is a product. Or if it's endothermic. Endothermic reactions, heat is a reactant. So we treat these as the same. So if this is at equilibrium, if we cool it, we remove heat. If we remove heat, we're moving product. If we remove product, this is going to shift to the Right. It shifts right. So if we cool this, it shifts right. Remove heat. Let's look at number 36. Heat is a reactant here. If the temperature is increased, we're adding heat. So the more heat we add, the more reactant we have, and it's got to shift it to the. So if we add heat, increase the temperature, it's going to shift this to the product side. We got to reduce that. It's too much. And so if the temperature suddenly increases, it shifts it to the right or forward. What will happen to the concentration of chlorine? If this shifts forward, the chlorine concentration goes up. If your purpose were to increase the yield of sulfur trioxide in the equilibrium, so we want more sulfur trioxide, would you use the highest or lowest operating temperature possible?
Low.
Yeah, low. We want low temperature. That way we remove heat, so we can shift this to the right and increase the amount of sulfur trioxide. And so it's best to do this reaction at lower temperature to get a better yield. The yield for that particular reaction isn't very good anyway. Now, here they don't show it on the product or the reactant, but they tell us delta H is negative. If delta H is negative, is that exothermic or endothermic? This will be exothermic. We're losing heat. So if we're losing heat, then heat is a product. If heat's a product, then if the temperature is suddenly decreased, we're removing product. If we remove product, which way is this going to shift? To the right. It's going to go forward. What will happen to the concentration of iodine? The concentration of iodine will go down. Then I did it wrong. This is an exothermic reaction. HI is more stable. I think I did that right. 39. The solubility of calcium hydroxide is low. It reaches about 2.4 times 10 minus 2 molar at saturation. In acidic solutions with many H plus ions present, calcium hydroxide is quite soluble. Explain this fact in terms of Le Chatelier's principle. So, for this one, we're going to see how things shift. When calcium hydroxide solid is placed in the water, some of it dissolves. And what we're going to do is we're going to reach a saturation limit. Once we hit that saturation limit, then we've reached a state of dynamic equilibrium in which, well, this is a salt, in which I guess you could say the population of the product and reactants will be stable. And so this is going to be at equilibrium. The first forward arrow will be dissolution, the reverse will be crystallization or precipitation. However, if we add acid, that's going to upset this equilibrium. If we add acid, then what happens is the acid will attack the hydroxide. H plus like OH minus. So if I have two hydroxides and I add two H pluses, do you know what I form? Just water. So I'm going to form two H2O liquids. So adding acid removes hydroxide. If I remove hydroxide, which way will this shift? To the right. If I shift this to the right, then more calcium hydroxide dissolves. Eventually I can dissolve all of it. I just keep removing the hydroxide, and keep shifting this to the right. And then I can get the calcium hydroxide to dissolve.
Sometimes when you give the answer, I sometimes say it favors the product side, but because of the equilibrium reaction, is there a product reaction?
There is a product. The products are on the right, the reactants on the left. But since it's equilibrium, we don't know which side's downhill and which side's uphill. That we don't know. Unless we're given K. If K is big, it's downhill. If K is small, it's uphill. Going from reactant to product. Consider the following system in equilibrium. The production of CHCl2 is favored by the following. So I want to increase the amount of CH2Cl2, so I need to shift this to the right. So I need to know what will shift this to the right. Will increasing temperature shift this to the right? Well, this is endothermic or exothermic? Well, delta H is positive. If it's positive, it's endothermic. If it's endothermic, then heat is a reactant. And so if I increase the temperature, I'm increasing reactant. If I increase reactant, it should shift it to the right. And so that will, A works. B, increasing pressure by changing the volume. So increasing pressure by changing, I decrease the volume. If I decrease the volume, which side's favored? Yeah, nothing's going to happen. So decreasing the volume doesn't do anything. C, increasing the volume doesn't do anything. D, adding CH2Cl2. If I add CH2Cl2, which way does it shift? To the left. So that's not going to do anything. E, removing CCl4. If I remove CCl4, that's going to shift it to the left to compensate for the loss reactant. And so the only thing that will work is A, increasing the temperature. This particular. So those are Le Chatelier's. So those are the types of problems we see for equilibrium. Chapter 19, we're going to move on to. And chapter 19 deals with redox. And for redox, we talked about redox reaction with electron transfer. So 19.1 we talked about. Yeah. 19.2 voltaic and electrolytic cells. We haven't talked about that. 19.3 here, oxidation numbers and redox reactions. We already did those. Oxidizing agents, reducing agents. We did that. Strengths of oxidizing agents and reducing agents. We already did that. Predicting redox reactions. We already did that. And then this comparing redox to acid base. I'm not even going to do that. Writing redox equations, this is optional. We haven't done this, 19.8. This is skeleton redox. So pretty much I want to focus on voltaic and electrolytic cells, and I'm writing redox reactive equations. I might not test you on this. Probably not, because I was going to try to finish this up today. I didn't make it through 19.8 this morning. So not to overwhelm you for the final, so probably won't have that on there. But you'll have some stuff with voltaic, actually electrochemical cells. There are two types of electrochemical cells. The first type of cell is the voltaic or galvanic cell. Same thing. The voltaic or the galvanic cell is what we call spontaneous. Redox reaction. It's downhill. This happens naturally. And it's what we call batteries. These are batteries. The other type of cell is called the electrolytic cell. The electrolytic cell is non-spontaneous. So for electrolytic cells, we have to force these reactions to occur. And so the redox reaction is forced using external power. External power might be an external battery or external power supply. For electrolytic cell, there are typical applications for these. This would be the application for a voltaic cell, would be a battery. But the typical application for electrolytic cell is recharging secondary batteries. Or synthesizing unstable higher energy, is what I mean, unstable chemicals or products. And electroplating metals. We could use voltaic cells to electroplate also. Galvanic cell gives us less control. Voltaic cell gives us less control. This is the battery setup here. So let's take a look at redox reaction here. The redox reaction that we're going to look at is this: zinc solid plus copper 2 sulfate. What does this yield? Zinc solid plus copper 2 sulfate. Yeah, zinc sulfate. Is that spontaneous or non-spontaneous? Spontaneous means it has a driving force present. Non-spontaneous means there's no driving force present. Yeah, speed is kinetics. It could happen fast, could happen slow. But when we're interested in thermodynamics, driving forces are thermodynamics. Which way's downhill, which way's uphill. And so in this particular reaction, we expect, well, we compare the two, zinc versus copper. Which one is a more stable metal? Zinc. Zinc is in the middle of pennies. Copper is on the outside of pennies. Yeah, so copper actually protects the zinc. Zinc is more reactive. If you put zinc on the outside, the copper penny wouldn't last very long. Copper would be on the inside. Actually, the copper of the copper penny wouldn't last. The zinc wouldn't last very long. So there's a driving force for this reaction. And so this is what we call a redox reaction. This is the CE, the complete equation. What's the IE for this? The ion equation going to be. Zn 2 plus what? Plus Cu2 plus plus SO4 2 minus. Does that look right?
No, when you put this in a mold,
Yeah. Right. This shouldn't be an ion. This should just be solid zinc metal. And then what are the products here?
copper metal, so this is Cu.
Yeah. What about this? What happens with zinc sulfate?
Zinc 2 plus and SO4.
And then copper, which is just the metal. Okay, that looks right. Okay, this would be the ionic equation. The net ionic equation will look like what? Zinc solid.
And copper into zinc 2 plus.
This would be the net ionic equation. This is a redox reaction. In a redox reaction, there's an oxidizer. Does the oxidizer take electrons or does the oxidizer lose electrons? Oxidizing something else means giving the electrons to something else. Like what's a good oxidizer? Oxygen? Does oxygen lose electrons? Or does oxygen take electrons? It takes them. And so oxidizers take electrons, reducers lose electrons. So what is the oxidizer here? Is zinc the oxidizer? It's taking electrons, or is copper 2 the oxidizer?
Copper 2.
Yeah, copper 2 is the oxidizer. Because we're going from copper 2 plus to copper metal. In order to go from copper 2 plus to copper metal, how many electrons did it have to take? 2. And so we go for copper 2 plus 2 electrons is going to give us copper metal. And so this is our oxidizer. Our oxidizer I call OA, stands for oxidizing agent. Who loses the electrons?
Zinc.
Yeah, zinc. And so zinc is our reducing agent. Reducers lose electrons. And so in this case, zinc solid goes to zinc 2 plus 2 electrons. So each zinc atom will lose 2 electrons. Or a mole of zinc atoms will lose 2 moles of electrons. This will be our reducing agent. Now, what happens is, who got oxidized? You know, copper 2 is our oxidizer, but did copper 2, our oxidizer, get oxidized? No. Our oxidizer oxidizes something else, so who got oxidized? Zinc got oxidized. Zinc got oxidized by our oxidizer, copper 2. And so we call these half reactions. And this half reaction on the bottom with zinc is called the oxidation half reaction. It's called the oxidation half reaction because zinc got oxidized by the oxidizer, copper 2. And this half reaction we call the reduction half reaction. Because the copper 2 was reduced by the zinc. reducing agent. And so there's a way to try to remember this, and that's oil rig. Oil stands for oxidation is loss of electrons. So our oxidation half reaction loses electrons. We lose electrons as a product here, so zinc loses electrons. Rig stands for reduction is gain. So the reduction half reactions here, because copper-2 gained electrons. And so this is our reduction half reaction. The reduction half reactions for our oxidizer, and the oxidation half reactions for our reducer. And if we add up these two half reactions, we get the net reaction. That is, we can combine the oxidation and the reduction half reactions, and then we get the net redox reaction. The net redox reaction, the two electrons cancel here, and we end up with this. So what we use batteries for is to generate electricity. And electricity is just the flow of electrons. So what happens here is if I take my zinc and mix it with the copper-2 sulfate solution, then the electrons are transferred directly. The copper-2 will attack the zinc, take the electrons straight from the zinc. But in a battery, what I need to do is I need to separate the oxidizer from the reducer. And so what that means is I'll put a piece of zinc here. This is going to be zinc solid in one beaker. And then in another beaker over here, I will put the copper-2, which is my oxidizer. And what I need to do is I need to have the electrons go from zinc to copper-2 through a piece of wire here. Okay, the way the electrons are going to go, they're going to be fed into the copper-2 by using an electrode. Electrode is just some conductor, like a piece of metal. That's our electrode. In this case, I want an inert electrode. An inert electrode is just going to feed the electrons to the copper-2. And so what are good inert electrodes? Probably the best inert electrodes, platinum. Why platinum? Platinum is very unreactive, and it's a metal. Metals have loosely held electrons, or metals have a sea of electrons. Sea of electrons here. If we recall the electron sea model for metals. Another common inert electrode is gold. Well, platinum and gold are kind of expensive. So what's cheaper than platinum and gold? Graphite. Graphite actually conducts electricity too. And so graphite's a pretty good electrode. The problem is any of these electrodes, if you feed electrons to copper-2, what is the product? So we're going to use the electrode to feed the electrons to copper-2. The product is going to be copper solid. And so what's going to happen is I'm going to get copper-plated platinum, copper-plated gold, and copper-plated graphite. Do I want that? No. So instead, I'm going to use the best material for this particular electrode will be copper solid. Copper solid is going to be considered inert because if there's a tug of war, copper versus copper, who will win a tug of war, copper versus copper? Copper will win. And so there's going to be no change. Therefore, copper versus copper, it's good. So copper is inert in this case. In other cases, if I had a more powerful oxidizer, copper will not be inert. Because a more powerful oxidizer will hit the copper. But I definitely don't want to use zinc, because if I use zinc over here, then the copper 2 will just attack the zinc directly and heat it up, right? What happens is the copper 2 attacks the zinc directly and heats up the zinc metal, and I'm left with zinc ion solution. So what copper 2 is going to do is it's going to pull on the sea of electrons here, and it's going to cause a ripple. But that ripple is not, it's not going to be successful, really. Well, this copper electrode's attached to copper wire, and so the sea of electrons continues here. And so the ripple here is going to be felt all the way here. This is copper. And so the electrons are all in copper until I hit the zinc. When I hit the zinc, now copper ions are powerful enough to oxidize zinc. And so I'm going to form Zn2 plus in air. Zn2 plus in air is not stable. That's going to build a huge static electricity charge. And so if you've ever been shocked by static electricity, then this is going to be a nasty shock. So what's going to happen is it's going to stop. This is not stable. And so instead, what's more stable is if I generate zinc ions in water. If I generate zinc ions in water, then the waters will hydrate the ion and help stabilize it. And so the oxygen end of waters will hydrate around zinc, help stabilize it. And so I'm going to add water here. And so what's going to happen is this. Copper 2 is going to pull on the electrons. That pull is going to be felt all the way to zinc over here. And so what's going to happen is, well, copper 2 is strong enough to oxidize it. And so it's going to pull off the electrons here. Those 2 electrons are going to get fed over here to the copper. And the 2 electrons will combine with the copper to precipitate out copper solid. And so over in this beaker, we have the half reaction. Copper 2 plus 2 electrons yields copper solid. And then over here, we're going to just use zinc as the electrode. This is called a reactive electrode. And so electrode is going to transport the electrons. And in this particular case, zinc is a metal that can transport the electron, but zinc is also a reactant, so this electrode is going to be eaten away. That is, zinc solid goes to zinc 2 plus 2 electrons. So what happens is this is one way we can transfer the electrons externally through a wire. We keep the oxidizer over here on the right, the reducer on the left, and we transfer electrons. Electrons should flow left to right. But what's going to happen is this. Over in this beaker, we're going to get positive charge buildup. The positive charge buildup is because we're forming zinc ions, but we're not forming any anions. The hydration, waters of hydration will help stabilize it, but it's not enough. Over in this beaker, we're consuming copper 2 ions, but we're not generating any new cations to replace those. There's going to be sulfate in here. And the amount of sulfate stays the same. Sulfate's just a spectator. And so what's going to happen is the negative charge buildup here. And as the positive charge builds up in this beaker and the negative charge builds up in this beaker, it creates a voltage. This is called a space charge. Space charge. And the space charge is not stable. It's going to create a higher and higher voltage. And as it creates a higher and higher voltage, it's going to stop the reaction. all together. And so the space charge buildup stops the reaction. And so this isn't going to be very successful at generating electricity because we're just going to get way too much positive charge here, way too much negative charge here. So to eliminate the space charge buildup, there's one more piece. To this battery. And now one more piece is called the salt bridge. In that figure over there, the salt bridge contains potassium sulfate, but it could contain any salt. This is going to be potassium sulfate aqueous. Any salt will work. Because what's going to happen here is as the zinc forms, a sulfate's going to migrate into this. So for every zinc 2 plus that forms, one sulfate ion enters the solution to neutralize that charge. Well, that will result in a space charge buildup in the salt bridge, but it doesn't. Because for every copper 2 that reacts, 2 potassiums will go into this beaker. So I'm losing copper 2, so I'm losing a 2 plus charge. I'm going to make it up by adding 2 potassium ions. That way the sulfate can be neutralized. And so if I have 2 potassiums going to the right and 1 sulfate going to the left, then the salt bridge maintains electrical neutrality. And it's going to maintain electrical neutrality in these so we don't get a space charge buildup, which stops the reaction. So that's what's shown here. At this electrode, zinc is being oxidized to Zn2 plus. Then Zn2 plus has to be neutralized. Then it's going to be neutralized by having sulfate in this potassium sulfate salt bridge migrate into this beaker. Since sulfate is an anion, and the anion is migrating to this beaker, we call this electrode, the zinc electrode, the anode. The anode is where the anions migrate to. And so this electrode, the reactive electrode, here is the anode. The anode is where oxidation occurs. Oxidation generates electrons, and those electrons flow from left to right over to this electrode. This electrode is copper. And at this electrode, the copper's job is to feed the electrons to the copper ions. And so the electrons are going to be fed to the copper ions. The copper ion is going to pick up those 2 electrons and deposit copper metal onto this. As we deposit copper metal, we're eliminating cations here. As we eliminate, we have to make up for those lost cations. So for every 1 copper 2 that disappears in this reaction, 2 potassiums flow here. So the cations flow to this electrode, and therefore we call this electrode the cathode. The cathode is where the cations go. The anode is where the anions go from the salt bridge. At the cathode, we have reduction occur. And so here's where we consume the electrons. So the oxidizers on the right, the reducers on the left, and we have electrons left. And so this electrode's named the anode. The anode is where oxidation occurs, and oxidation produces electrons. Those electrons flow where they're consumed at the cathode. So this is the cathode, and cathode is where reduction occurs, where we consume the electrons. What's pulling the electrons through is the copper, the oxidizers. The oxidizer copper 2 is pulling the electrons through the wire. As we pull the electrons through the wire, you can power devices, electrical devices like a light bulb, shown there. Depending on how strong the pull is, there's a tug of war here. We generate a voltage. Like the voltage. And the voltage for this particular cell depends on the concentration. So if we have 1 molar here, it's 1.1 volts. If we go to 6 molar copper 2, we're going to get this higher voltage, more oxidizer. Oxidizers taking electrons. 1.1 volts, the voltage is the force on the electrons through the wire. So the higher the voltage, the more force there is in the flow of electrons through the wire. So anyway, battery, we just use the redox reaction to generate electricity. Electricity, we can use to power electrical devices. So here are some examples of batteries. This would be a nickel cadmium battery. Nickel cadmium battery would be rechargeable, so this is a secondary battery. A lithium battery here, this is rechargeable, but the construction of this is quite a bit different. Lithium would be the anode here, lithium metal. Manganese oxide, this is the oxidizer here, that's the cathode. Primary batteries aren't easy to reverse. So if I wanted to recharge this battery, what I can do is I can hook up a power supply here or another bigger battery. So if I hook up a power supply, what I'm going to do is I'm going to force the electrons to go backwards. If I force the electrons to go backwards, then it's going to reverse both of these. And it's just going to have the reverse reaction over. So I can recharge this battery by putting a power supply here and forcing the electrons to go right to left, which is non-spontaneous. Spontaneous would be left to right. This is an example of an electrolytic cell. So here's an example of an electrolytic cell here. In this electrolytic cell, they're forcing the electrons to go right to left by using a power supply. In this case, the power supply is battery. So what they do is they hook up the positive terminal power supply here. And the positive terminal is sucking the electrons in. And then the negative terminal is forcing the electrons out. So let's take a look at this electrolytic cell in more detail here. So I don't have enough time. Let's do this real quick. So in an electrolytic cell, I want 2 inert electrodes. And then I'm going to put some kind of power supply here. In the power supply, there's going to be a positive and a negative terminal. The positive is sucking electrons in to the power supply. This one I'm going to make out of platinum. And this one I'll make out of platinum. So I'll have 2 inert platinum electrodes here. And so at this electrode, we're going to oxidize species that's easiest to oxidize. Platinum's hard to oxidize. And so that's why we use platinum here, so we don't oxidize the electrode. This is an inert electrode. And so we have to look at what's in contact with the electrode. In this particular case, they're using molten sodium chloride. Molten sodium chloride is NaCl liquid. NaCl liquid consists of sodium ions liquid and chloride ions liquid. And so in this particular case, sodium ions we aren't going to oxidize, but we can oxidize chloride ions. And so over at this electrode, we'll have two chlorides go to a chlorine plus 2 electrons. Chlorine's a gas. And so over at this electrode, we're going to generate chlorine gas. And so in this case, we're not recharging the battery. In this case, we are making reactive products. Chlorine is a very reactive product, and chlorine is very stable. And so the chloride is going to come in here, generate chlorine gas, and those 2 electrons are going to be fed to the power supply. So we might have to crank up the voltage for this, because it's going to be hard to take the electrons off chloride. Chloride's stable. But we can crank up the voltage on this, because the power supplies have adjustable voltage. And so if we crank up the voltage high enough, we can strip the electrons off chloride. And then the electrons are going to be forced out the other end. And over at this end, we're going to reduce the species that's easiest to reduce. And so the situation here is the species that's easiest to reduce is going to be the strongest OA present. The species that's easiest to oxidize will be the strongest RA present. And so sodium ions aren't a reducing agent. Chloride's the only reducing agent we have here. But however, sodium ions will be the strongest oxidizing agent. And so over at this electrode, the only thing that will consume the electrons will be sodium. Sodium ions will take an electron to form sodium. Sodium is usually solid, but this is molten sodium chloride, so it's high temperature. So that means the sodium is going to be liquid. And so what we're going to have here is we're going to have liquid sodium. Liquid sodium is less dense than sodium chloride. So we're going to build up liquid sodium over here. That is molten sodium metal. Now, we don't want molten sodium to come into contact with chlorine, because if molten sodium comes into contact with chlorine gas, we're going to get an explosion. So we have to have a divider here that separates the chlorine from the sodium. And so overall, this reaction, we'll have to double this. But the net redox reaction is going to be 2 sodium ions plus 2 chloride ions is going to give us 2 sodium metals, liquids, and chlorine gas. That's not a favorable reaction. That's terribly uphill. But this is an example of electrolysis reaction here. All right, we're out of time, I think, so we'll stop here. I'm going to talk on Monday. I'll talk about one more electrolytic cell for the electrolysis of water, and then the skeleton redox.
I have a question.
Uh-huh.
How do they have liquid sodium chloride?
Yeah. They have to heat it to high temperature. Sodium chloride melts at around 700, in the mid 700 degrees Celsius range. So they just have a very powerful furnace to melt sodium chloride. It's hard to melt this stuff. So this is very expensive if you want to do this, because you need a lot of fuel to electricity to electrolyze it. And so it's an expensive way to make it.